Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good day for Mr. Fajar and also everyone who watched this video. So my name is Areta Yasmina Luthi with student ID 2043. Now I'll be presenting my course summary on carbon absorption for volatile organic compounds or VOCs as a control technology in air pollution engineering. And this presentation is based on the EPA Air Pollution Control Cost Manual by 6th edition of 2002, that commonly referred to as the VOC manual. Then I will walk you through 6 main sections in here: an introduction to adsorption, the types of adsorbers, adsorption theory, and isotherms, the design procedure, and also capital cost estimation and annual cost estimation. So, adsorption, as we know, that is a surface phenomenon in which VOC gas molecules are physically attracted to and retained on the surface of activated carbon through van der Waals forces. And because of this physical nature, the process is largely reversible, which is a key advantage of this technology. And as VOCs accumulate on the carbon surface, heat is released and making it exothermic process. However, approximately 3 to 5% of the VOC undergoes chemisorption, bonding chemically to the surface, and cannot be recovered during regeneration, and this permanently reduces the carbon's capacity over time. Then, why we use the carbon adsorption? So, there are 4 main reasons this technology is selected. First is effectively removes VOC from low to medium concentration gas streams. And then second one is achieve the outlet concentration down to part per billion by volume or ppbf levels. And third, the captured VOCs can be recovered and reused or sold, which offsets operating cost. And the fourth, it is widely applied in printing, chemical, and also pharmaceutical industries. And one important safety constraint in here, the inlet VOC concentration must not exceed 25% of the lower explosive limit, or LEL, to prevent fire hazard inside the bed. And there are 2 main categories of carbon adsorbers. The first one is the fixed bed unit. So the fixed bed units are the most common configuration. They handle gas flows from several hundred to over 100, 100,000 CVM. And then in continuous operation, the more common mode, at least 2 beds run in parallel while one bed adsorbs VOCs, the other is simultaneously being regenerated with steam. And the desorption cycle takes approximately 1 until 1.5 hours. After steam injection, the bed must be dried and cooled before returning to the surface. And the EPA recommends regeneration every 8 to 12 hours for optimum performance. And then the second one is the canister units. The canister units are designed for smaller or intermittent emission sources, such as storage tank fans, and they range from 55-gallon drums up to 2,000-pound vessels. And unlike fixed bed units, the canisters are not regenerated on site. They are replaced on or returned to the vendor when exhausted. And to prevent the VOC breakthrough, the canisters are often arranged in series, so the second unit acts as the safety backup. And the standard system from the TIGG Corporation handle up to 30,000 CFM. And for the adsorption theory, we had this Freundlich isotherm. To design a carbon adsorption system, we need to know how much VOC the carbon can hold at equilibrium, and this is described by the adsorption isotherm. And for activated carbon system itself, the type 1 of isotherm's shape is typical, which is convex upward, that meaning the capacity increases rapidly at low pressures and then levels off. And for the Freundlich equation itself describes as a this formula where the W is the equilibrium absorptivity in pounds VOC per pounds carbon, and then the P is the partial pressure of the VOC in this unit, and then for the K is and M are the empirical constants. And then for this is the several concepts that we need to be aware of. And then for the design procedure, so for this first step is we need to determine the sizing parameters. So we define the design basis, the volumetric flow rate, inlet and outlet VOC loadings, desired adsorption time, working capacity, and also gas humidity, since the moisture competes with the VOCs for adsorption sites. Then the second one, set adsorption and also desorption times. Select the adsorption time and also desorption time, which ensures the adsorbing baths are always ready for before an adsorbing bath reaches the breakthrough. And then for the third step is estimate the carbon requirement. The carbon mass per adsorbing bath is this formula, and then for this fourth one we can do the we can apply the working capacity rule, which is the working capacity is estimated at approximately 50% of the WE, that maximum, and evaluated at the inlet VOC partial pressure using the friendly isotherm. And then the total capital investment is built from the following components. So for the carbon cost itself is by this formula, and actually this reflects economies of scale, that larger vessels cost more but not proportionally. Then the equipment factor, this one, and then that accounts for fans, pumps, condenser, and decanter. Then this one is for the total equipment, and this one is for chase equipment cost, and this one is also for the total capital investment. Okay, so as you can see below, so to give a sense of the cost breakdown itself, the carbon is about 6% of TCI, and the vessels is 15%, the auxiliary equipment 13%, direct installation 33%, and also the indirect cost is 34% contributed. And then for the next one is the annual cost estimation. So we can calculate the total annual cost by the direct cost plus the indirect cost minus the recovery credits. So direct cost itself include the steam at this pounds of VOC recovered, and then cooling water for the condenser, electricity for fans and pumps, carbon replacement every 5 years, operating labor at 0.5 hour per shift, and maintenance. Then the indirect costs include the capital recovery, the property taxes at 1%, the total cost investment per year, and then the insurance, and also the overhead of total labor, the system design life, that giving the CRF about this value. And then the recovery credit. This is the most often underestimated term, that the for total when the credit is approximately like $0.027 for a pound recovered. And if ignored, the TAC can be nearly doubled and significantly misrepresenting the true cost. And this is the work example. The parameter is as we can see in here, and then the value of the problem parameters. So what is actually showing from this problem? So this example showing that a well-designed carbon adsorption system achieves about 98% VOC removal at a moderate total annual cost, and especially when recovery credits are properly accounted for. And finally, we jump into the summary and also conclusions of this presentation. So to conclude, the principle of the physical van der Waals adsorption of VOCs onto activated carbon is reversible, except for the 3 until 5% approximately chemi-sorption fraction. And then the system types. The fixed bed for large continuous operation, and the canisters is suitable for the small or intermittent sources. And the design itself, the carbon charge governed by working capacity, VOC loading, and also adsorption time, and then the capital cost dominated by carbon and fossil cost. And the annual cost, the major items was steam, and also capital recovery, and also overhead that's significantly offset by recovery credits. And the best practice is we can regeneration, do the regeneration every 8 until 12 hours to support both cost efficiency and also pollution prevention. And that concludes my presentation today. The full reference is from the Fatafok et al. EPA Air Pollution Control Cost Manual, 6th edition of 2002. Thank you very much for your attention. I'm happy to answer any questions if you had, and I will close this presentation with salam because I also open with salam. So, Assalamualaikum warahmatullahi wabarakatuh.